Thanks for tuning in today. I'm excited to introduce our seminar speaker this week, Dr. Klimczak, who is currently an associate professor at the University of Georgia in Athens, which is just a short drive from here. So maybe next time we can actually have Dr. Klimczak here in person. He is a structural geologist slash planetary geologist whose research mainly focuses on studying fractures and faults from really the microscopic scale to the landscape scale, not only on Earth, but also for other planetary bodies, mainly Mercury, the Moon, and Mars. And he takes a very interdisciplinary approach to his research, combining lab, field, remote sensing analyses, and also numerical modeling in his work. And I would say anything involving fractions and faults, Dr. Klimczak is really into. And so he's originally from Germany, where he did his undergrad and master's studies at Freie Universität in Berlin in geology or geological sciences. He then did his PhD at the University of Nevada in Reno in 2011, and then a postdoc at the Carnegie Institute or Carnegie Institution in DC from 2011 to 2014. And then in 2014, he started his tenure track position at the University of Georgia in the Department of Geology. And today, as I mentioned, he's really interested in a lot of topics, but today he's going to be sharing some of his research on Mercury, presumably from data from the MESSENGER mission, which I'm excited to hear about. And so with that, let's welcome Dr. Klimczak and take it away. Thank you again.
Right. Let me share the screen and activate the laser. Okay, so I hope everybody can see the screen at this point, and I want to thank you for inviting me and giving me the opportunity to present some of the most recent number crunching I did for the planet Mercury. So some of you may remember me because I visited the department maybe when I was really new at UGA, and I previously presented on the general geology of Mercury because this was my expertise that I recently developed at that point, with my postdoctoral fellowship working at the MESSENGER mission. And so today we have come a long way of analyzing the geology of Mercury, and today I am presenting on some global tectonic patterns that we are trying to understand, decipher, so to speak, on the innermost planet. First up, before I forget, I want to thank all the people that have over the years worked with me towards developing the global tectonic map of Mercury. So Kelsey, Ishik, Paul, and Jupiter all have been instrumental in either developing the mapping techniques, actually mapping, or discussing and testing the technique as guinea pigs, so to speak, on multiple planetary bodies. And obviously, I also need to thank NASA and the University of Georgia for giving me the funding or the time to conduct this research post-MESSENGER. All right, so our innermost planet, Mercury. So we have been exploring Mercury with a very few spacecraft. If you're used to Mars or the Moon, you know that there is tens of spacecraft that have visited or landed on these bodies. But for Mercury, we have only 3 spacecraft that will be visiting or have visited the innermost planet. The very first one was the Mariner 10 mission that in the mid-1970s flew by Mercury 3 times, and we approximately imaged to an okay resolution the planet by 45%. And it wasn't until the MESSENGER mission and that we got images of all of the planet. 99+% of the planet was imaged by the MESSENGER mission, and we had multiple instruments on the spacecraft, and the mission operated in orbit, in a polar orbit that got us really good resolution on the North Pole and less detailed images on the southern hemisphere. But it was a polar orbit that got us some high resolution images for part of the planet. And very interestingly, we have ESA's and JAXA's spacecraft, Bepi-Colombo. And this is currently on the way. We had previously a Venus flyby already, and surprisingly, next week, we will actually have our very first Mercury flyby. So the third spacecraft will visit Mercury next week, October 2nd. So I'm sure the people from JAXA and ESA are really, really excited about flying by Mercury for the first time. But aside all the different scientific discoveries, I want to focus today on just mentioning a few general aspects of the innermost planet. First of all, in terms of the geology, and if you look at this limb shot of Mercury here, you can already assume that it is a heavily cratered body. Okay, so we have lots of impact craters of different sizes. But I also want to draw your attention to some areas here that are less cratered. And we know that they are resurfaced by volcanic activity. And you can also see here in this area, we have a really, really bright spot with a dark pit in the middle. That is an actual explosive volcanic vent. So we have a rich history in volcanism on Mercury. And then you may also notice several of these linear structures across the surface of the planet, and they occur anywhere you look, but they're easier to be seen in the smoother areas. These are tectonic structures, and this is what I will focus on in the remainder of my presentation. So why do we have tectonics on Mercury? Because, like on Earth, we know we have plate tectonics, and that drives a lot of the deformation that we see at the surface of our planet. But Mercury is a one-plate planet, and so we do not anticipate there to be any plate tectonic activity. But Mercury is a planet with a very large core. Okay, so we know that Mercury has a very large core and a relatively skinny mantle. So basically, if we drill down Mercury, we would, after 400 kilometers of depth, we would already be in the core. And upon accretion, and there were some radioactive elements in the interior, Mercury had a lot of heat. Okay, and the heat that Mercury had is basically trying to be cooling over the lifetime of the planet. And so due to the cooling of the planet, we started shrinking Mercury. And that is one of the major drivers of tectonic activity. We refer to this process as global contraction, so the shrinking of the planet. And we have thermal modelers or interior modelers and also geologists looking at the surface assessing the amount of global contraction, and we frequently report that in the radius change. And both the thermal modeling and also the mapping of thrust faults on the surface both indicate that Mercury may have contracted from, some people say 1 to 2 kilometers, but others range all the way up to around 7 kilometers. And the primary outcome of shrinking will be thrust faulting across the planet. And since the shrinking is expected to be occurring in all dimensions equally, we expect a random pattern of thrust faults from the process of global contraction. Then other processes are also suggested to have taken place on Mercury. For example, tidal despinning is one of the processes. In this chart here, where Mercury revolves around the sun and rotates around itself, you can see that actually Mercury is locked in a tidal resonance with the sun, where for every 2 resolutions around this, or revolutions around the sun, Mercury rotates 3 times. Okay, so this is a relatively slow rate of rotation at this point, but we actually know from geophysical measurements that Mercury has probably rotated similarly fast than Earth or Mars before it got locked into this resonance with the sun. And based on the calculations of the slowing of the rotation, we have identified that there should be a pattern of structures, and if tidal despinning occurred by itself, it should have been opening mode fractures, so fractures like joints, cracks basically, that have a latitudinal pattern. And the pattern is mostly east-west oriented jointing. But tidal spinning could have overlapped actually with the process of global contraction, and so global contraction would still be overpowering all the other processes and form thrust faults. So thrust faults would be expected to have also a latitudinal pattern if global contraction and tidal spinning overlap to some extent. And then there is a bunch of other planetary processes that could cause tectonics, such as planetary reorientation. Okay, so we have several large impact basins on Mercury. We have several large low-lying areas, and people have proposed that reorientation is actually combined with any of the other processes, also capable of producing different types of patterns, and all of them depend on the amount of reorientation and the direction of the reorientation. And then last but not least, the process of mantle convection has also been investigated as having contributed towards producing certain orientations of thrust faults on Mercury. But when we look at the size of the mantle, we are not entirely sure if mantle convection was ever a process or is currently ongoing on Mercury. It's possible. Several models indicate that it could or it may not be possible, or it may not be happening. But depending on the mantle convection pattern, where the downwelling and the uprising of the mantle occurs, we may be able to preferentially form structures also along those lines. Okay, but the main takeaway point here is that global contraction produces thrust faults on Mercury. That's the main driver of tectonics, and any other overlapping process that we find on Mercury has the potential to actually influence the orientation of these faults. Okay, so moving on to what type of landforms can we see on Mercury's surface? And here are just two block diagrams, really simple block diagrams of the types of landforms we may observe on Mercury. And so we have on the left side here a negative relief landform forming a trough, which is normally interpreted as a downdrop block that is likely forming a graben. Sometimes graben are actually formed when they're underlain by dikes, but currently for Mercury we do not have any detailed topographic information that would allow us to detect a dike with numerical modeling. And so we assume that at this point, either one, normal faults or dikes, produce a graben by means of the strain extension or extensional strain. On the opposite end of the spectrum, we have shortening strain, which is expressed on Mercury or on any of the inner planets that we observe as a positive relief landform. So in this case, we have a gentle backslope rising towards a ridge and then dropping sharply and asymmetrically towards a surface break. Okay, and this scenario is interpreted as being underlain by a thrust fault. And I will bring a few examples in just the next slide, so you have an opportunity to see what this is actually like on Mercury. So looking at extension, as a nice field example, this is one of my field site and the Needle section of Canyonlands National Park. This is an air photo, a shot from a helicopter down onto the graben area of the Canyonlands National Park. So there is several negative relief landforms in Canyonlands National Park that allow us to study the geology and also use it as a planetary analog towards troughs on other planets, including Mercury. So we visited the site in the field, and we actually look at, in this case, the negative relief landform in this image. And one of my students here is for scale in the foreground, standing on what we term a relay ramp. Okay, so this scenario is where we have two trough landforms, actually stepping over from one landform and onto the next, and we have several faults bounding these landforms. And based on the landform that we see here, the relay ramp, we have a distinct criterion to say that this is definitely a normal fault, because relay ramps are actually indicative or diagnostic of normal faults. And they form because at least two normal faults that overlap in their map pattern with one another have tapering displacements towards their tip, forming this nice gentle slope where the displacement tapers out on one fault, but increases on another fault, forming this really nice ramp. If we then see those planetary images and find relay ramps, we can definitely say that those are actually normal faults. So we have two examples of negative relief landforms on Mercury shown here. One is from inside the Caloris Basin, and you can see that aside from this impact crater, we have several landforms. And sometimes, I know it's hard to actually interpret gray scale images because you may see it inverted. So always keep in mind impact craters have a negative relief, and the shadow indicates the way we have downward. And so this is a negative relief crater. And also the troughs have the shadow on the same side. That means that they are also negative relief structures. But if you look really, really close here, there is several areas where we can actually note overlaps and relay ramps being visible in the images. All of these types of graben have been mapped by Byrne et al. And published. In the other parts of Mercury, we actually have flooded impact craters. So this is basically a flooded impact crater here, a larger one, superposed by a fresh impact crater. And the flooded impact crater is indicated by a round ring of a ridged ring. But inside this ridged ring, we have very small troughs. And those troughs don't show any relay ramps, so we don't really know if they are indeed bound by normal faults. But at this point, we are including them as our negative relief landforms as an extensional landform on Mercury. And all of these troughs were mapped by myself in 2012. And these play a role later for compilation of all of the data sets into the global tectonic maps of Mercury. Okay. On the opposite end of the spectrum, we have shortening. Okay, and so just as a field example from Earth, this is the Umtanum Ridge in Washington State, and this is located in the Columbia River flood basalt in the Yakima Fold province. So this is a really nice analog for studying thrust fault related landforms on other planets, and we can visit an actual volcanic area that has been faulted and a flood volcanic area that has been faulted, similar to what we actually observe on Mercury. And if you really look closely, you can see the individual units of the basaltic flows here in the side of the mountain. And if you look carefully here, you can actually see that they're curving and forming a relatively shallowly dipping limb on one side, on the right side of the image, but then we're curving towards a very steep limb towards the left side of the image here. And so we know that the very steep limb is very close to the surface break of the thrust fault that is underlying this whole folded set of basalts. And so we assume that similar processes fold and fault the rocks on Mercury. And one very nice example, and you can probably guess who was involved in naming the structure, because I worked at the Carnegie Institution of Washington. This structure is Carnegie rupees. Rupees is the descriptor term that at International Astronomical Union descriptor term for scarps that are underlain by thrust faults. And And the naming scheme here actually very interesting is ships of exploration and discovery. But what you see is a surface break of this image, and then the color coding indicates the topography or elevation. And we can see at the surface break, we actually have a high standing area on one side and a low laying area on the other side. This really illustrates that along this surface break of this thrust fault that cuts through several craters, we actually have formed and uplifted the topography to form up to 2 to 3 kilometers of relief on these landforms. And this is in the northern hemisphere, so we actually have really, really nice resolution. So we can zoom in and look at the details of the thrust faulting. So in this case, this crater here, which is located inside another crater, is shown in this point, and the thrust fault is actually really nicely overriding the crater and then interacting also with smaller craters on other portions of the image here. This shows us that this thrust fault, looks very crisp and very fresh, that this thrust fault probably is very recent or has very recent activity on it. And when I say very recent, I would say, well, it may be in the last 1 billion years. This is the level of detail we can say things from Mercury for sure. But it would be actually interesting to send a lander on Mercury and put a seismometer on it and see if there is actual thrust faulting going on at the present time, because Mercury is probably still cooling. The core has some liquid outer core probably that is still cooling and probably actively forming in the inner core, and for that reason Mercury is probably still shrinking and therefore should have some active thrust faulting on the innermost planet. Okay, all of these thrust faults were mapped by Byrne in 2014 and Crane and Klimczak in 2019, and they will also be compiled later on in the global tectonic map. But I also add, as a tectonic structure, impact craters. Okay, so especially the rims of impact craters. Here is a field example from Meteor Crater in Arizona. So we have a satellite view of Meteorite Crater in Arizona. And if I had to ask you the question, what is the shape of this impact crater? Is it round or is it square? Okay, so if physics tells us that if this rock is an anisotropic material, the impactor would basically be a point source, and all the geologic processes would be radial or concentric to the point source and form a perfectly round impact crater. But I hopefully don't have to have a hard time to make you look at the actual rim and convince you that this is actually more of a square. Okay, and so the reason why meteor impact crater or meteor crater is a square shape is because there is actually some fractures in the rock units into which the impact occurred, and the rock fractures in this case are oriented in this southwest northeast and northwest southeast orientation. And during the impact, then these fractures were utilized to form the rim. And when we go back to Mercury, and here just a few examples of the heavily cratered planet, we can actually observe multiple types of impact craters that definitely are not round. If you draw a circle, you get huge mismatches, and you may be able to spot certain straight edges, very straight segments of the rim of these impact craters. And you can see it also in the background image. Many of these impact craters are not perfectly round. And another point that I want to make is that it matters also on the degradation stage on the impact crater. Okay, so we have a very heavily degraded impact crater here. We have a moderately degraded impact crater here, and then we have a very fresh impact crater here. And it becomes easier to see that there's straight rims part of the fresher impact craters, but even in the heavily degraded craters, you can see that this may or may not be perfectly round and only mapping would indicate whether there is a straight rim or whether this impact crater is polygonal. So this is just like a random cartoon I found on the internet showing us the basic concepts of impact cratering. So at first, we have the contact and compression stage where the impactor actually hits the target, and that's basically the stage where the shockwave is released. But in the second stage here, which is the excavation stage of the impact cratering process, material is basically ejected away from the site of the impact. And if we have a pre-existing fracture system in the subsurface of Mercury, then we can actually take out or preferentially excavate along fractures. And in the third stage of the impact process, we may also have basically mass wasting preferentially, or formation of the impact crater rim preferentially along pre-existing fractures. So mapping impact craters may actually help us understand the fractures that are hidden otherwise and we cannot resolve with traditional photogeologic methods. Okay, so my method, so I had the option of actually telling you a lot about my methods, but I think they're really not that interesting and I want to get to the results, so I will make this with 4 bullet points. Okay, so what I did with my collaborators is compile all of the tectonic data sets that we have available for Mercury and make it into one coherent data sets and make the mapping that was carried out by different people consistent with one another by several algorithms that I ran to simplify and split the data apart. Then I also mapped all craters together with my collaborators on Mercury and analyzed which segments of the crater rim are actually qualifying as straight rim segments, so we can utilize them as analyzing them as pre-existing fractures in the lithosphere of Mercury. And then, to cutting a really long story very short, is we then computed and analyzed the orientation data. Okay, and so the overlying questions I pose here for this presentation is, are there regional or global tectonic patterns displayed by faults on Mercury? And the same question goes for the craters. Are there regional and global tectonic patterns found by assessing the straight rim segments of craters? And then if we find tectonic patterns between the two data sets or among the two data sets, how do they compare with one another? Okay, so jumping right into the results here at this point. We are looking at a Mercury dual imaging system global mosaic of the innermost planet, where we have the volcanic regions outlined here in this very line faint green. So we can see that there is some volcanic activity or flood volcanism occurring in the northern hemisphere, and then there is a large impact basin that is volcanically flooded, and there are some smaller impacts. They are not really that small, they are still large impact basins, but compared to the Caloris Basin here, which is the largest impact basin, this is the main area of volcanic resurfacing that we have alongside the northern volcanic plains. But let's plot all of the compiled faults on top of this map. In beige, all of the extension is highlighted, and you can see that in beige the extension is mainly located in large impact basins such as the Caloris Basin and maybe here in the Rembrandt Basin. Then a few small impact craters have some extension, and then across the northern smooth plains we have some of these volcanically flooded impact craters that had some of the troughs inside of them. But the vast majority of tectonic structures that we found on Mercury are shortening structures highlighted here in magenta. So you can see that they occur on the entire planet. There is areas in the volcanically flooded regions that are actually a little bit more dense in terms of the fault density. But generally speaking, these are a global population of thrust faults. And when we look at patterns, so what kind of patterns can we see here? Well, we can actually look at some patterns already from the tectonic map. So we can see that there's linear chains of thrust faults that go through Mercury for several tens of degrees of longitude and latitude, or thousands of kilometers. And then we have other patterns where these thrust faults actually outline the rims of larger impact basins or craters. But really, in order to make sense of the data, we have to statistically compute the orientation and display it in Rose diagrams. So what we did was then we actually used all of this data and accounted for the projection and accounted for the length of each individual structure and produced length-weighted Rose diagrams for all of Mercury. At first, I will show a random binning of 30 by 30 degrees of latitude and longitudinal binning. And so this is what we did. We split and mapped all line segments, computed the strike of each line segment, accounting for distortions caused by the projections. We then binned all the segments into geographic regions and plotted the orientations in Rose diagrams. And this is the final map of our distribution of tectonic landforms. So a Rose diagram, for those of you who are unfamiliar with Rose diagrams, this is giving us circular orientations of directional data as a circular histogram. And we plot the orientation from 0 to 360 degrees, with north being 0 degrees, south being 180 degrees, east 90 degrees, and west 270 degrees, and anything that falls in between. And we also we did a statistical analysis to find out what is the optimal actual bin size for each Rose diagram to highlight a pattern, to highlight the strongest modes of each of the Rose diagrams. And so all of these Rose diagrams have different colors and have different binning inside of them for highlighting some patterns. The density of the structures is the color. So bluer Rose diagrams have fewer observations, and green to yellow Rose diagrams have a higher amount of data in them. And now we are looking at the pattern again, and I would, I'm still puzzled looking at this map. I know that there is some north-south orientations, there is some east-west orientations, there is some different orientations to be seen here in the data. But what's the pattern? Okay, so one thing that we can actually notice here is that in the northern hemisphere, or at the North Pole and at the South Pole, we have to some extent east-west patterns and different patterns on top of that. But what's striking here is that in the mid-latitudes and equatorial regions, all of these Rose diagrams have almost no east-west oriented structure. And some of you may now raise your hands and say, oh, this could be lighting bias. But we have mapped on hillshades. We have mapped on hillshades that were illuminated such that we avoided an east-west lighting bias. And we can more or less rule out a lighting bias, and this is a real pattern that we observe on Mercury. Now comparing this to the straight rim segments of impact craters. So we have a method that we followed where we identify an impact crater and then manually map it. Okay, some of you who are really good with machine learning may say that machines may be the better way to go, but we are mapping these impact crater rims, assuming that a planetary geologist would be able to actually identify the correct outline of the impact crater rim. And we followed a special procedure where we really try to not bias ourselves with the scale or with the mapping by automatically placing vertices and removing those vertices that did not contribute to the overall shape of the impact crater, and in the end isolating only those segments that would be identified as straight. And yes, this method is not 100% perfect, because everybody raising their hand saying that there's a straight rim segment here still that we haven't mapped. But in the grand scheme of things, we mapped over 6,900 craters on Mercury. And I think that forgetting one or two straight rim segments may not be statistically relevant. Okay, so now looking at all impact crater rims, and obviously this does not look like a pattern at all. This seems randomly distributed in terms of the actual straight rim segments, but we can see that there is areas with more impacts, and then there's areas with fewer impacts, such as the resurfaced areas here. But it is very interesting to plot the orientation of the impact crater rims. And so again, we computed the strike of each straight segment, binned the segments into these geographic regions at first, longitudinal and latitudinal bins, and then plotted the orientation as rose diagrams. And this is the map for impact crater rims. Okay, color coding is the same. The rose diagrams, the way they are computed, are exactly the same, and the underlying data is basically everything is the same. And so in this case, we can see that the orientation of impact crater rims is, again, at the poles here, more or less east-west oriented. And then we have, I cannot make a pattern here. There's some regional variations where we have predominant north-south patterns, or maybe somewhere east-west patterns as well. But in general, in the mid-latitudes, I would say that we don't have any discernible obvious patterns that stand out. Okay, so when we compare all of these observations with one another, we can actually combine these as the global tectonic map of Mercury that involves impact craters highlighting hidden fractures as well as the observed shortening and extensional structures. And comparing the patterns can be done in any way you want to slice Mercury up. So in this case, I sliced it up only by latitudes and only by longitudes and compare the patterns. And so in magenta here are all faults, including normal faults and thrust faults. And in this greenish color here, we have impact craters again. And you can notice that there's really not a comparison. You can't really say that they match anywhere. So at the poles, we have random orientations for faults, but east-west orientations for craters. And binning everything together in the mid-latitudes and equatorial regions shows us that we have basically random orientations of impact crater rims and north-south orientations of thrust faults. And longitudinally, this is very monotonous. Faults have a tendency to be north-south oriented, whereas impact crater rims have a tendency to be actually randomly oriented. And so my takeaway point here is really that yes, we have latitudinal and longitudinal dependencies in the data. The pattern is not very clear, but that there is lots of regional variations that we have in both data sets. And so I decided the latitudinal and longitudinal binning that we chose was basically arbitrary. So we chose those 30 by 30 degree bins without really saying that there is a geophysical or geologic reason for it, other than maybe the tidal despinning aspect. So what we did was recenter the tectonic map onto the Caloris Basin for just testing if maybe the Caloris Basin has an impact on the tectonic pattern. It's a large impact. When it impacted, it probably has a big damage zone, and some of the damage zone of the impact basin may actually be utilized later by faults that formed by global contraction. And we then binned 30 by 30 degrees bins around the Caloris Basin. So the Caloris Basin is one bin, the antipode is the opposite bin, and then we have all of these different bins around the Caloris Basin. And in this case, we extract all the fault data and plot all the fault data. And this is what we have. So one of the things that stands out to me is that the north-south pattern that we observed in the previous map is not as apparent. Okay, so basically the rebinning shows us that there's many different other patterns that we can see. And the question was, how much of this pattern is actually radial or concentric to the Caloris Basin? And it also doesn't really jump out too much to me, although there is certain bins where you can say definitely radial to the Caloris Basin in certain bins, in certain areas. But in other areas, we really don't have something that I find a good match. So I isolated the radial and concentric patterns, and it looks like that in green we have concentric patterns. There is some, in green we have radial patterns, that there is some match in the data, and in pink we have some concentric patterns around Caloris. But this is like right now arm waving, so I don't really have a statistical method of saying that this is definitely related to the Caloris impact. But we can actually do the same analysis for craters. So if it was definitely a pattern, a fracture pattern introduced by the Caloris Basin, some of the impact crater rims should pick it up. Okay, and so we separated the observations of impact craters into very heavily degraded impact craters and fresher impact craters, and only the fresher impact craters should be able to utilize the fracture system that potentially the Caloris Basin may have introduced into Mercury. And for that reason, we have we can compare the pre and post Caloris impact craters, again with the binning, and it's hard to do this manually, by just looking at the data. And so the takeaway point here is for me that really you can look at bins, and some bins have the actual same orientations. So I would say we can discard the hypothesis that maybe the Caloris Basin has had an impact on the fracture patterns for craters, and comparing now faults and crater rims is a future task where we do this statistically in order to maybe find individual modes that we have for the data. And as a takeaway point here is that, yes, there is regional variations, radial and concentric to Caloris, but we need qualitative data comparison, quantitative data comparison. And bringing me to my very last topic here, the Caloris Basin is actually very close to the Mercury's hot pole. Okay, so it's the last concept I promise, and then I will be done. So we are looking at a temperature distribution of the planet Mercury, and we can see that there is areas in the equatorial regions that are hot. Okay, we call those the hot poles. And then towards the actual poles, we actually get cold temperatures. And this is also related to Mercury being in this 3-2 spin orbit resonance with the sun. And we can actually say, does this hot pole, cold pole situation have an influence on Mercury's tectonic pattern? As previously proposed, there is a thermal insulation that may cause strength differences in Mercury's lithosphere. And also, obviously, there is some tidal pulling that is caused by this resonance. So we actually binned Mercury's tectonic map again according to hot poles and cold poles and look at the data. Okay, so again, we have some of the rose diagrams being oriented in parallel or perpendicular to the bins, showing that there could be some orientation where it is actually the thrust faults are wrapping around the hot poles, and then inside the hot poles it is harder to see. Some of them may have actually radial and concentric components as well, but we can see that in general the trend is very promising, but also not a slam dunk pattern. Comparing this to the craters, also no slam dunk pattern. So we're still deciphering what really causes some of the observations of the tectonic patterns on Mercury. And yeah, the comparison is needed. Qualitative comparison really doesn't tell us very much, but I promise there will be some statistical comparison. And so fault orientations are concentric to hot poles. And as a takeaway point here is that there seems to be no obvious pattern in the crater data from just visual inspection of the Rose diagrams. So in conclusion, I hope that you guys agree with me that there is some complex patterns actually found on Mercury, both in crater and fault data sets, and that I would say several processes must have operated on Mercury either in concert or in succession that caused the observed orientations of structures. I know for future work, this is what the emphasis is here, is that statistical comparisons are needed to identify correlations between the orientations of the data sets. And we also haven't really, distinguished between different types of the data. So we can do more geographic binning, or we can do separation of fault types. And then bringing up the last question, have we investigated all different types of tectonic processes that could influence orientations of faults and crater rims? And my answer is probably not. So, and with that, thank you everybody, and I am open for some questions.